Hi everyone, let's look at some variations. For example, let f of x equal 1 over the square root of x squared minus 9. So when is this real? I want to know the domain of this function. Find the domain of f. I want to know the real values of x for which this is real. When is this thing real? This thing is real if and only if the radicand is what? Strictly positive. It cannot even be 0. You're not allowed to divide by 0. The radicand must be strictly positive. So we have to solve this strict inequality. X squared minus 9 is greater than 0. No bar. So how does our domain change? How is the solution set different from before for this inequality? You exclude the endpoints here. So you have parentheses next to the -3 and the +3. Let's look at the graph of that. What is the graph of that thing? Y equals 1 over the square root of x squared minus 9. All right. Look at this. It turns out we get VAs at x equals -3 and x equals +3. Right? The domain, again, we get these very negative numbers. We get these very positive numbers. We don't get the numbers near 0, and we don't get 3 and -3 themselves. We have VAs there at x equals 3 and -3. And we have open parentheses for the domain. What happens with our various methods? All right. Well, in the sign chart method, I don't want the actual endpoints at -3 and +3. I don't want where the product is 0. In the parabola method, I don't want the x-intercepts. I don't want the 3 and the -3. Don't want these. In the test interval method, I don't want where x squared minus 9 is 0 itself. But I still want the wings. We want open parentheses here. Same for this. All right. But that was the difference. Open parentheses. We don't want where the radicand is 0. Trick question. F of x equals the cube root of x squared minus 9. Quick. What's the domain? The domain, the implied domain of the domain of an odd root of a polynomial is assumed to be all reals. No restrictions. Because the domain of a polynomial is assumed to be all reals, and cube roots never cause a problem. Whether the radicand is positive or 0 or negative, the cube root's fine with that. For example, the cube root of -1 is -1. The domain is all reals. Hey, if g of x is the 11th root of a 40th degree polynomial, what's the domain? It's all reals. We love odd roots of polynomials. Of course, whenever the radicand's messed up, it's messed up. If you have the cube root of 1 over x, say bye-bye to x equals 0, but that's not a polynomial. All right. Look at this now. Let's say that I ask you to solve the inequality x squared is greater than x. I want to know all real numbers whose squares are greater than themselves. Now, a lot of students are thinking, hey, I'd love to divide both sides by x. Do not do that. Do not divide both sides by x. That's very risky. Why? If x is negative in value, what do you have to do to that symbol? You have to flip it. So in order to do that, you might have to split into cases where x is positive, where x is 0, where x is negative. So just in general, it's a bad idea to divide both sides by a variable expression, unless you're sure it stays positive. All right. So instead of doing that, let's isolate 0. subtract x from both sides, isolate 0 on the other, and then it becomes a sign analysis problem. We like turning things into sign analysis problems. Factor, and by the way, we have to factor over the reals, all right? We're factoring over the reals. Because when you consider the potential x-intercepts, every real 0 corresponds to an x-intercept. So we want to factor over the reals. All right, factor over the reals, we get x times the quantity x minus 1. All right, quick, parabola method. The graph of y equals this guy, or this guy, the factored form, parabola opening up. The x-intercepts are at 0, 0, and at 1, 0. I want to know where the values of y equals x squared minus x. I want to know where the values of this thing are positive. So I want to pick up, I'll make this piece hairy. I want to pick up the pieces of the parabola that are strictly above the x-axis, not the intercepts themselves. There's no bar here. So I want to put open circles here. I want the real values of x that are negative or greater than 1. Negative or greater than 1. This is the solution set to both these inequalities. And this makes sense. Intuitively, it makes sense. You could use a test value method. Okay, we want numbers whose squares are bigger than themselves. Well, of course, if you take a number like 1 million, the square of a million is bigger than itself. We want these numbers. But the square of 1 is equal to 1. It's not greater than 1. I don't want the 1 itself. Likewise, the square of 0 is 0. The square is equal to itself. I don't want the 0. Now, what about 1/2? The square of 1/2 is 1/4. But wait, 1/4 is not greater than 1/2. I don't want these values either. But wait a minute. The square of every negative real number is positive, isn't it? Every positive number is greater than every negative number. For example, the square of -3 is greater than -3 itself, because the square of -3 is positive 9. Every positive number is greater than every negative number. So all the negative real numbers work. Intuitively, this makes sense. We want all negative real numbers and all positive real numbers greater than 1. Numbers like 1/2, their squares are less than themselves. All right. And again, in really weird situations, you might get all real numbers or the empty set. Right. For example, the square root of opposite x squared. The domain for that is the empty set. You're just dead everywhere. Actually, not everywhere. Oh, I should have done this. Because x equals 0 would have worked. There you go. For all real values of x, this thing is guaranteed to be negative. The domain for this thing will be the empty set. All right. That's chapter 2.